Hey everyone, my name is Matthew Fleming, and today I have an interesting problem regarding the relationship between pressure and temperature of a closed system. So in this problem, we have a container filled with 1 kilogram of water, and it's open to the atmosphere. The container is then sealed with the contents inside at 298 Kelvin and a single bar of pressure. We want to find the required temperature to increase the pressure to 2 bars and the appropriate volume so that at this pressure there are 0.3 moles of water in the vapor phase. So first we're going to write down the variables that we're given so we can better understand how to map out this problem. So we have the initial pressure is equal to 1 bar, which is equal to 100,000 pascals. And the final pressure is equal to 2 bar, or 200,000 pascals. We have the initial temperature is 298 Kelvin, and the mass of the water as 1 kilogram. We want to find the final pressure and the total volume of the system. So first, we're going to try and find the temperature required to get the pressure from 1 bar to 2 bar. And to do that, we're going to break down a couple different equations. And one of these equations that we'll need is the ideal gas law. So first, we need to mention that the total pressure of a system is equal to the pressure of the vapor plus the pressure of the liquid in the system. And in this case, the vapor is going to be the air plus the pressure of the liquid, which is the water. And the pressure of the water can be looked at as just a function of temperature. And we can use that function in Python. So that one's actually pretty easy to find. And the pressure of the air gets a little bit more complicated, but we can intuitively look at a model and better understand how to deal with it. So if we look at our model, so we have water in the liquid phase and air up here, right? And we're given all the values that correspond with the system right as it's closed off from the atmosphere. And so we know that when you close a system of liquid and vapor and it is sealed into a closed system, it's going to work towards an equilibrium. And so as time goes on, water in the liquid phase is going to leave and go into the vapor phase. And it's going to do this until a equilibrium is reached. But at the point in which it's just been sealed, this process hasn't started yet. And so we can actually find the number of moles of air in here and thus the pressure of the air by taking this into account. So we know if we break down the pressure of the air, let's say the pressure of the air is equal to the number of moles of air times the gas constant times the temperature divided by the volume of the air. Now, we don't know the number of moles of air and we don't know the volume of the air. To find the number of moles of air, like I said, we can use the initial values to solve the ideal gas law for N here. So we can break down, we'll solve for N, number of moles of air. It's going to be equal to pressure times volume divided by gas constant times the temperature. But we can't use this at just any arbitrary point. It has to be at the very beginning because at the very beginning, like I said, nothing up here, no water exists in the vapor phase just yet. And so if we use the initial values, we're actually going to find the number of moles of everything that's not liquid, and that's going to be the number of moles of air. And so we can use the initial pressure and the volume of the vapor because, again, we're trying to find the number of moles of vapor and the initial temperature. And so this is going to give us our value for here, and then we can plug that in to find the pressure of the air. And like I said earlier, the pressure of the water can easily be found because we'll just use a Python function that will give us the pressure of any amount of water at whatever temperature we decide to put it at. So we can actually set it as just a function of temperature. And so now what we have here is the total pressure of the system is equal to the number of moles of air times the gas constant times temperature all over the volume of the air and plus pressure of the water at any specific temperature, and it's equal to 2. And so the only thing now that we need to find is the volume of the air here. And so we can say that the volume of the air is equal to the volume, the total volume, minus the volume of the water. And to do this, we can actually just find the volume of the water because we're given its mass, and we know the volume is equal to mass over density. And we can just assume 10 liters of the total volume of the system here. So we're going to set the volume of the air is equal to 10 liters minus 1 kilogram mass of the water divided by rho of the water. And that's just the density. So now we have a equation for the volume of the air. And we can plug this in and this in to this equation right here. And now this is really good because now we have the total pressure of the system as just a combination of two different functions of temperature. And so now what we'll do is we'll tell the computer to then vary the temperature until this equation is solved. And that will give us the temperature required to get the pressure to 2 bars. It's really cool. Now if we want to find the volume of the entire system, and here we just assume 10 liters. But we don't want to do that because now we want to know exactly how many liters it would take so that when the pressure of 2 bars is reached, we have 0.3 moles of water in the vapor phase. So now we're going to draw back some of our previous equations. The pressure of the system is equal to the pressure of the air plus the pressure of the water. And we're going to leave the pressure of the water as just the function of temperature. And we know that pressure of the air is equal to the number of moles of air times the gas constant times the temperature, all divided by the volume of the air. And we know that the number of moles of air is equal to the initial pressure times the volume of the air divided by the gas constant times the initial temperature. And now we know that we have a constraint here, and we want to know that we want to guarantee that 0.3 moles of water vapor are in the system. And so we can simply just solve the ideal gas constant, or ideal gas equation for the number of moles here, and we can set it equal to just the water vapor moles. So we'll say, so we know that N is equal to PV over RT, and we want to only take into account the water vapor moles. So we can say the number of moles of water vapor is equal to the pressure of the water, which again we have as just a function of temperature, times the volume. And because we're only taking into account the water vapor, so we want to find the volume of the vapor here, which is the same as the volume of the air. And we will divide that by the ideal gas constant times the temperature. And so now we've actually again found the number of water vapor moles as a function of temperature, because the only thing that's varying here so far is this pressure function and the temperature down here. And we want to set this equal to 0.3 moles. So what we're going to do is similar to the last problem up here when we found the required temperature to reach 2 bars. But instead of just varying the temperature now, we're going to vary a couple other things, one other thing to be exact. And so first of all, we'll set up our equation. Volume of the air is equal to the total volume minus the volume of the water initially. So it's going to be the same thing as up here. So the volume of the air is equal to the total volume minus mass H2O all over the density of H2O liquid. So we're only taking into account the liquid here. So we can take this equation right here is going to solve for, well, there's 2 unknowns. So the volume of the air is unknown because we don't know the total volume here. We only know this term here. And so what we're going to do is we're going to set up 3 different equations here, and we're going to have 2 different variables that will then be varied. And we're going to have the computer vary these variables until all 3 equations are satisfied. So first of all, we'll set up our first equation. Total pressure is equal to number of moles of air times gas constant times the temperature, all divided by the volume of the air, plus pressure of the water as a function of temperature. That's going to equal to 2 bars. So we're going to have this equation. This equation is going to have 2 different variables varied until it equals 2 bars of pressure. Now, the second thing we need to do is, well, we have this term here, and instead of just assuming 10 liters of the total volume, we're now working so that we can try and find the actual, a real satisfiable value for that total volume. So it's not gonna be a fixed equation anymore. We need to vary this whole equation here. So we're gonna say volume of the air is equal to the total volume minus the volume of the water. And of course we know the volume of water, but we don't know these 2 values. We don't know this value because we don't know this value. And so this equation we'll come back to here in a second. This third equation is really where we solve, really where we get this problem done. So we're going to have the number of moles of water vapor, and like we said earlier, it's equal to pressure of the water times the volume of the air divided by the gas constant times the temperature. And it's equal to 0.3 moles. So these 2 functions, we know they're equal to a specific value. We don't know what this equation will be equal to just yet. So what we can do is we can actually take all 3 of these equations and we can vary temperature and the total volume so that when we get, we'll vary the temperature and the total volume so that this equation is satisfied by an appropriate temperature and total volume of air, and so that this equation is satisfied with an appropriate volume of air and an appropriate temperature. And I will go over how we do that exactly in the programming video I upload next so that we can truly find exact values on how to solve this problem. Thank you.